start the home stretch of the gene function annotation cozy. So thank you all for sticking around. Just remember, there's a poster session for us and for the others. So many of the talks here are accompanied by posters. So if you want to continue drilling deeper, deep learning, please go and talk to the authors. And some don't have some that don't have talks have posters, so that's great. Like for me, the organizers didn't want to take my talk, so I do the poster. You're welcome to see as well. And we have two proceedings papers this session. And first one is from Yannick Mahlich from the Technical University of Munich, who will talk about HFSP, high-speed homology-driven function annotation of proteins. Thank you.
Thank you for the introduction, and I'm very excited to open this afternoon session. So I'm going to talk about HFSP, which is, as Ido already said, a method for high-speed homology-driven function annotation of proteins. But before I dive into the actual HFSP, I want to reiterate on two things that are very important to me. And that is, we have an extremely rapid growth of available protein sequences. This is very apparent if we're looking into Tremble, the unreviewed part of UniProt. And especially if you look into the last 3 years we have more than duplication of available protein sequences in there. And then secondly, and more importantly, if you look at the same trend in trend graph for SwissProt, what you can see is that since about 2010, there has barely been any change in terms of the numbers that have been added into SwissProt. And what that reveals to me is that, well, first of all, we obviously need some computational methods to deal with the influx of data that is available. But secondly, we also need more experimental validation of the proteins since we're building on that knowledge to actually do our predictions. And to illustrate that further, if you look at all of UniProt, the first thing that, well, should be apparent to you here is that 98% of the proteins in UniProt are actually proteins that have never been seen before. So those are either completely predicted or transferred via homology. And only about 0.5% of all of those proteins are in SwissProt, which is supposed to be the well-annotated and curated part of UniProt. If I'm dissecting that further, you will actually see that only about 20% of those proteins in SwissProt are actually proteins with an experimentally validated existence, which means that our whole knowledge of the protein world is based on those roughly 100,000 proteins. And since I was specifically interested in enzymes, I dug a little bit deeper, and of those 20% of those roughly 100,000 proteins, only about 10% are actually proteins or enzymes with an experimentally verified function. So the first two takeaways for you is our knowledge is based on an extremely small subset of known proteins. And secondly, if we're looking specifically for enzymes, only about 9,000 proteins of those are actually enzymes with an experimentally validation. And that's less than 0.01% of all of UniProt. So let's get to HFSP. HFSP stands for homology-derived functional similarity of proteins. And at its heart is an evolution of HFSP, which originally was developed by Cressander and Reinhard Schneider and used to transfer secondary structure based on protein homology. And then in the late 1990s, early 2000s, Burkhard-Rost showed that you can also use this to transfer enzymatic function. Our specific goal was to replace SciBLAST, which is the major bottleneck of HFSP, with a much, much faster alignment method called MMCX2, which was developed by Martin Steinegger. And in the process of re-optimizing the curve, we also extracted a new set of proteins, a new set of enzymes, with an up-to-date classification of enzyme function. So in a nutshell, the thing that I want to do with HFSP is determine whether two proteins share the same function, yes or no. And to get to that goal, I go back to those 10% of proteins in SwissProt, my experimentally verified enzymes, and I'm doing a little bit more filtering. Specifically, I take only those enzymes where we have one EC annotation and that enzyme classification is completed on all 4 levels. And then we have redundancy reduced all of those sequences to 98% sequence identity, which left me with 6,835 enzymes. As I said, we used the enzyme classification as like the reference point to determine whether two proteins share the same function or not. EC is, as many of you might know, a hierarchical classification scheme where each consecutive level describes the enzyme function in more detail. And what we observed is that in our set of roughly 7,000 enzymes, we actually do not have enough enzymes with the same EC annotation such that we could optimize our method to create proper results. So we decided to only go for the third EC level and do our optimization based on that. So what we're doing is we're creating an alignment between all of the enzyme pairs of those 7,000 enzymes, place them into a two-dimensional space that is spanned by sequence identity and ungapped alignment length, those two values we extract from the alignment, and then we color our enzyme pairs by the knowledge whether those enzymes share the same function or not. And the next step is to create a gradient decay curve that optimally separates that functional identity, those functional identity classes. The formula you can see in the bottom right here. And then as soon as we have that gradient decay curve, we define that everything above that gradient decay curve is of same function, everything below is of different function. So putting everything together, what we can do now is we have our protein that we're interested in, we have a sequence database, and then with that HFSP measure in combination with MMSeqs, we can determine whether those two proteins share the same function or not. Visualized here. So my recipe for HFSP. Just to summarize, we extracted, as I said, the experimentally verified enzymes. We place them into our two-dimensional space and then optimize a gradient decay curve to separate those experimentally identified function classes. So how well does this work? Well, if we're looking only at the third EC level, we get an actual quite good performance with 92% precision at about 64% recall. The dots here are the precision and the triangles the recall. And that is at our default threshold of HFSP 0. Things are getting a little bit more complicated, however, if we're looking into determining whether two proteins share the same function on the fourth EC level. And what you can see here is that we have an immediate drop of performance down to 45% precision at the default threshold. So what that led us to think about is, well, are people really interested whether two proteins share the same function, or are they rather interested in what is the functionally closest protein to the protein that I'm looking at? And what we did here is, instead of looking at all possible enzyme pairs, we're only extracting the result with the highest scoring HFSP. And if we're looking at the precision here, you can immediately see a 40% increase. The thing that I want to point out here, though, is that the recall is based only on those high-scoring HFSP scores. So if we were going back to our previous slide, and we're looking at the corresponding precision, that would mean that we're looking at a recall of about 23% if we're considering all possible pairs. So having said that, we wanted to see how the HFSP distribution actually looks for proteins in SwissProt that are not experimentally verified. So everything with an EC annotation that is not in our reference. And to do that, we started breaking down our enzymes in the HFSP reference at first to get like a point of reference. And what I want to show you here is, as I said, we have 6,835 enzymes in our reference. Of those, 5,518 enzymes are enzymes with a non-unique EC annotation. And we're looking here at the fourth level. So that means that those 5,000 proteins, 5,500 proteins, are proteins where we observe that specific EC annotation multiple times in our reference. On the flip side, that also means that we have about 1,300 enzymes in our reference that do have a fourth level EC annotation that only appears once in that reference. We're only considering results with an HFSP score bigger or equal than 0. And what I'm displaying here, the only disclaimer that I want to give here is the percentages and the bars are based on the full 6,835 enzymes. I'm only showing the bars for the non-unique EC numbers, though, to reduce complexity of the graph. So the first thing that we can observe is we have a very small fraction of mispredicted enzymes. Again, on the 4th EC level. And secondly, for about 8%, which is made up of 4.5% of proteins with an HFSP score smaller than 0, and 3.5% of proteins that did not generate an alignment to begin with, those 8% of enzymes, for those we cannot make a prediction. And if we're now looking into our remaining enzymes in SwissProt that do have no experimental, but do have an annotation in SwissProt, the first thing that we actually can observe is that 15% of those enzymes do have an EC annotation that is not observed in our reference, which begs the question, where is that annotation coming from, if that is an annotation that we have never experimentally verified. And then secondly, 19% of those enzymes could not be annotated. So this is a more than twofold increase over our reference, and that leads us to believe that there is a large fraction of potential misannotation in SwissProt. So having established that, we were asking, okay, how good are we actually then at identifying novel functionality? And to do that, we approximated unknown enzymes by looking at the SwissProt, the reference enzymes, with a unique EC annotation, and we approximated our known enzymes by looking at those enzymes with an EC annotation that appears multiple times in our reference. And the first thing that we observe, if we're looking at the distribution of HFSP scores, is that this distribution of HFSP scores for enzymes that are known and correctly predicted, that this distribution is bimodal. And my intuition would tell me that we are looking here at enzymes with a very close homolog to the right side, and on the left peak we are looking at enzymes that have a homolog in the reference that is maybe a little bit more distant. Secondly, if we're looking at the known enzymes that are wrongly predicted, they tend to have a, on average, lower HFSP score than those that are correctly predicted, which is a good thing. The unfortunate thing is if we're now adding our unknown enzymes, we actually cannot really distinguish the unknown enzymes from the mispredictions. Good news, if we try to come up with a threshold that says everything, if we're considering everything right or everything bigger than that specific threshold, such that less than 10% of all of the predictions made are mispredictions or unknowns combined, then we're looking at an HFSP score of 14, and that should give us a relatively good idea where to look. And then lastly, since we have now looked at the enzymes that are experimentally verified and enzymes in SwissProt that do not have an experimental verification, we were all looking at all of the proteins in SwissProt. And the first thing that we observed is, well, out of the 290,000 non-enzymes in SwissProt, if we're running those against our reference set, for more than 250,000, we could not generate an alignment to begin with. So that's telling us that, well, we can distinguish our non-enzymes from our reference. And this distribution might actually look familiar, a little bit familiar to you if you were here for one of the earlier talks today. And then the next thing that we looked at is if we're now looking at all of the enzymes in SwissProt that are not experimentally verified, there is a difference between the distributions between the reference and those that are of complete EC annotation. So to make it a little bit more, visual, the reference are the proteins where we know what the function is, or at least that's the closest that we can get to known function. Whereas the complete EC annotation, those are those enzymes for which we think we know the function, but we have never shown that that actually is the function. And then lastly, I looked at the incomplete and multiple EC annotation, ECs. And what you can see here is that, well, it sort of falls in between our non-enzymes and our complete enzymes. So the incomplete and multiple EC annotations, that would be enzymes where we do not really know what's going on. And the point that I want to make here is that we might have a potential method now to pick like a range around HFSP 0 and drill down and see and like take out proteins and enzymes that might be interesting to look at further, to maybe experimentally verify such that we can then learn more and do better and more reliable predictions in the future. And that's what I want to close on with. So my last takeaways, we can tell you which proteins are not enzymes. We can accurately predict the enzymatic activity. And as I said, most importantly, we might be able to highlight enzymes, for example, for initiatives like the Protein Structure Initiative, to look at, and those proteins might be crucial to further our understanding of the function world. And the last two things that I want to leave you with is, first of all, we're currently in the process of building up a web service such that everybody can use this tool, which can be found at the first link. And then the second link is a resource to a organism microbial functional similarity database, and we're aiming at improving that database, increasing the data amount in there with HFSP and MMSeqs. And with that, I want to thank Professor Jana Bromberg, my advisor, as well as the whole lab, and Burkhard Rost and Martin Steinegger, who were very crucial in doing and helping me with this research, as well as the funding from NSF and the Technical University in Munich.
All right, thank you, Yannick. We do have time for a couple of questions. Okay. Please approach the microphone. Yes, thank you.
So, very nice work. I suspect your data set has some bias in the sense that when in the 80s or 70s or 60s, biochemists were not biased by sequence similarities. Mm-hmm. They didn't have that possibility to use that criterion, no? Yep. So many of your experimentally characterized enzymes were characterized because they were similar to other protein with the same function.
Okay.
So there is one very nice data set that you can use to test if your criteria is actually good for finding proteins with similar or different sequences based, or different activities based on sequence similarity, which is the so-called duplicated genes, homologs or paralogs. Mm-hmm. Have you used that data set?
We did not specifically look at paralogs and ontologs. Okay. We have looked at, let's call it outliers, though, where we have an extremely high sequence identity, but we're, for example, running into problems where they do not have the same EC annotation. But yeah, so at orthologs and paralogs, we have not specifically looked.
Orthologs and onologs.
Onologs,
onologs or
onologs.
paralogs?
Yeah.
Okay.
So there was a science paper about 3 weeks ago where they found a new enzyme in periwinkle, which is the last step in some cancer drug. Anyways, when I read this, I thought, how can we predict this, right? It's just like a totally wild thing. So, but do the EC annotations, do you have access to the dates that EC number was created in the first place? Because one thing I'd be interested in is just seeing sort of what different temporal slices look like in those histograms you made, because there could be some really interesting trend there.
Yes, that is actually something that I tried to look at. Unfortunately, it is not very easy to extract that data, so I was not entirely successful. What I saw, though, is that, for example, in comparison to the enzyme set that Burkhard Rost extracted about 15 years ago, for a lot of those enzymes in there, the EC annotation has actually radically changed over the course of the last 15 years. So something, where the enzyme was reclassified, or the EC category was reclassified. So for protein pairs or enzyme pairs that would have been predicted correctly or incorrectly for that matter, by the method 15 years ago, we might get, or we're definitely getting, different results today.
So you'd have to go back and like fix the old version of the database or something?
Which is really not that straightforward, yes.
Okay, thank you very much.